Oh, there you are. Yeah, well, I'm glad I found you. Obviously, I'm not in class this week. I'm in Chicago giving a presentation to the Portland Cement Association on life cycle assessment and life cycle cost analysis of rigid versus flexible pavements. Really great stuff. So this week we're going to cover excavations. It's the August 30th, 2016 lecture, which is a follow-up from last week's lecture on our very first day of class, where we talked about heavy construction in general and the basics, and we talked about the basics of earthwork. So this presentation tonight is going to be on earthwork, excavation, calculating volumes, cut and fill, production of excavation equipment, and a lot of other really good stuff. It's going to be packed with a lot of information. It's going to be concise because my presentations in class are designed to be interactive, where I can interact with you guys right on the board, do a little bit of entertaining, answer questions, get some feedback, maybe someone sharing experiences. So I plan my lectures to fill in a lot of time with important information related to what your interests are and questions related to my particular lecture. You feed students, there will not be a feeds tape available for you, because this is it. This will either be placed on YouTube or Vimeo or both. I haven't decided yet. You'll be able to see it over and over again. I'll give you access to it, and there won't be a 1-week limit like with feeds. Also, the PowerPoint presentations that I am actually presenting are being sent to you, or you probably should already have them. You can look at them while you listen to the presentation, or you can watch the presentation, go back and look at the PowerPoint presentation and take some notes, write down questions. Obviously, I can't answer your questions tonight, but I can answer your questions when we get back. We'll review what we covered in this particular presentation, and we'll try to answer some questions if you have any burning questions or anything. It's real simple stuff, but it is a lot of information. There is some nomenclature, and there are some vocabulary that you will have to know, a few formulas and so forth, but a lot of it is very intuitive, and you shouldn't have any problem with it. So in the meantime, I want you guys to sit back, watch this from home, put your PJs on, get a nice cold one if that's what you like, or maybe a hot cup of coffee or a hot cup of tea. Enjoy, just sit back, watch it with your family, entertain your friends. I'm sure it'll be very entertaining. So anyway, have a great week, be safe, and I will see you on September the, 4th or 5th, something like that. Anyway, see you soon. Take care. Welcome to continuation of our class. We will continue with Earthwork 3 for our heavy construction class. Last week we talked about heavy construction and the various aspects of heavy construction and some minor details about what earthwork might be. Remember, heavy construction will cover earthwork, paving, and other structures, a little bit about airport, and also about tunneling. As we continue, what are some of the earthwork activities? Excavation, cut and fill, and soil preparation and stabilization. We'll talk more about excavation and particularly about cut and fill. We'll spend a little bit of time on soil preparation and stabilization, both mechanical and chemical stabilization. This is an example of a cut and fill project. We can assume that this might be a roadway project that would be underway or in planning. We can see that the smooth curve up there at the top is what our intended grade will be, or our final grade, and the dotted lines represent what the existing grade would look like. Beginning at station 75.05, we will look at that there's a 2.88% slope there. What we want to do is we want to smooth this out so that we can have a smoother roadway with appropriate sight distances for stopping and for passing. Here the existing grade is a little bit rugged. and we're going to do something about that. So what do? Well, the best way to go ahead and do that is to remove this. We call this cut. This is the cut portion. And the most economical way is to use this cut portion as our fill, to fill in this area. We have three types of projects: cut projects where we remove more soil than we need. We have fill projects that require more soil to complete the fill program. And then we have a balanced program where our cut and our fill are equal. So in this particular case, we can estimate approximately how much material we are removing, and then we can estimate the amount of fill that we will need to fill this in to give us a nice smooth curve. Various types of cut and fill projects. We have, see in the darkened area, we have the area that we'll be cutting. We have an existing grade, or as they refer to it, as the original ground. This looks like it might be a roadway project where we'll remove this amount of material. We'll have embankment here on this side, or slopes, and then our pavement grade will look something like this. Here again we have a fill. We have a fill project where we'll be filling it to get a nice roadway profile here up above the slope of the ground. And all this would be to have a continuous and uniform grade for our pavement. Here we see that we have the cross slopes for the two pavements, as well as the ditch or the runoff slopes, which are much greater. Down here we have a combination cut and fill project. We'll be filling an area here, and we'll be cutting an area. And what we're doing here is we're filling one side, so that one side of the pavement, maybe northbound, would be filled, and this would be our center line. And then we have our slope for the pavement, and then we have the center line, and then we'll come back, and in order to achieve the same slope, we'd have a cut project. And again, as we leave off the shoulder, we'll have a greater slope to our runoff, for our runoff purposes. When we do cut and fill calculations, we need to know how much material we'll be removing and how much material we will actually need. So we'll do some earthwork volume calculations, which are good calculations, or estimates of the amount of material we'll need. And this goes to a lot of different things. Will the amount of cut that we have meet our needs for a fill? Will it exceed our needs? Or will we have a balanced project? Also, it's going to determine how many truckloads we're going to need, how many trucks will you need to haul the material, and to be sure that we have a continuous balance, so that we always have a truck ready when we're ready to dump the excavation from our front end loader, from our equipment on the field, and put it into the trucks. And they would in the same token, we don't want to have a lot of trucks waiting and sitting, because that hinders our production rate. And so we want to have a nice balance between the earthwork volume that we're removing and the truckload volumes that can be used to carry it away. So cross-sectional methods, there's trench excavations, and then there's the average end method. Of course, the average end method is an approximation method. Even more so than the trench excavations, we take advantage of some of the geometries and known applications of geometric calculations in order to estimate the amount of earthwork volume we'll be removing. For trench excavation, very simple. We have the volume is equal to the cross-sectional area times the length of a trench. The trench basically is defined as an excavation that is much longer than it is wide or deep. So we have a very long excavation that could possibly be maybe 3 feet or 6 feet deep, 3 feet or 6 feet wide, and the length would be somewhere in the area of 100 feet, 500 feet, 1,000 feet, whatever the requirement is. That would make it a trench. So in example 1, we say find the volume, which is the bank measure of excavation required for a trench 3 feet wide, 6 feet deep, and 500 feet long. Assume that the trench size will be approximately vertical. So this would give us a nice rectangular shaped trench that is 500 feet long. Bank measure is just the volume of material as it sits in the ground. So we have bank measure. Solution, the cross-sectional area would be 3 by 6, very simple, 3 feet wide by 6 feet deep. So we have a 3 by 6 or an 18 square foot face to our trench, and then we multiply that times 500 feet divided by 27 feet per cubic yard, and that would give us 333 bank cubic yards. The average end method, which was the other method of estimating the volume of a trench, it actually applies to whether or not the trench is rectangular or square throughout, or whether or not one end of the trench has a different cross-section than the other end of the trench. Here in this case, we'll assume that A1 and A2 are not equal, but this certainly applies if A1 and A2 are equal. The volume would be equal to the length, L, times A1 plus A2 divided by 2, which is just the average of the two, and then divided by 27 cubic feet per cubic yard. So we're converting cubic feet to cubic yards. We use cubic yards in earthwork because our dump trucks volumes are in cubic yards. So all this equation is that it's the average of A1 and A2 divided by 2. The presumption is that these would be straight lines, that we don't have various a lot of variety in the cross section, that it's pretty much straight line. We're assuming vertical sides here, of course, and so we're just taking the average of the two ends and using that as an approximation for the entire or an average cross section of the trench times the length, which would give us the volume in cubic feet. But then we'll divide by 27 cubic feet per cubic yard in order to come up with bank cubic yards. If A1 were equal to A2, basically what we'd have is 2A1 divided by 2, or 2A2 divided by 2, which would of course be either A1 or A2. That's why I say it doesn't really matter if the two ends are equal or not in cross-sectional area. This average end method would apply. Here we want to calculate the area between two end areas 100 feet apart. Assuming that A1 and A2 are not equal, and here in this particular case we do not have vertical sides, we have sloped sides. We have a slope to the side, and the reason we have a slope on this side is to prevent a cave-in. So we know what the friction angle of a soil is, and the cohesiveness of the soil and the friction angle would determine what slope we would need to prevent cave-in. In this particular case, we have the bottom is 2 feet, the height is 3 feet. At this end, the width is 2 feet, and the height is 2 feet as well. They give us what the angles are, so that if we need to, we can calculate the length of this side. Again, it's 100 feet long. This is an example of estimating the volumes. The volume of the fill between station 8 plus 00 and 9 plus 00. The end area at 8 plus 00 plus the end area at 9 plus 00 divided by 2, which would be the average, these two areas, times 100 feet, which is the length of our trench or our excavation, and of course we divide this by 27 cubic feet per cubic yard. This method can also be used for fill. In this particular case, it would be used as a fill volume as opposed to a cut volume. Again, here we're just estimating areas. We're estimating what the cross sections would be. Here we'd have the first area, the second area, third area, fourth area, and the fifth area. Actually, this would be the sixth area over here. A couple of formulas that we should remember. Of course, the formula for a triangle as the area is equal to 1/2 b plus h. I'm sorry, 1/2 b times h. 1/2 b times h, because b times h would give us the area of a rectangle. Divide that by 2, we get the area of the triangle from corner to opposite corner. Here in a trapezoid, it's a very similar formula. We have the area is equal to 1/2 the height times a plus b, which is really a better way to look at this formula would be h times a plus b over 2, because what we're really trying to do is take the average length of the top and the bottom. So it would be a plus h divided by 2 times h. I'm sorry, a plus b divided by 2 times h. That would give us the area of a trapezoid. Here's an example. We have 4 sides A, B, C, and D. What is the area? Well, we're given that A is equal to 12 feet, B is equal to 26 feet, C is equal to 25 feet, and D is equal to 25 feet. So what this tells us that because these two sides are equal in length, that our angles would be the same. And so that this distance of A and B right here, this difference would be, if we were looking at a triangle, we'd call it A plus B divided by 2. The height, using the Pythagorean theorem, where the d square would be equal to h square plus 1/2 of b minus a, which is what this formula says. So we're looking at the area is going to be, if we want to look at this distance here, okay, we'll be subtracting this amount twice from this area. So we'll have the Pythagorean theorem to calculate h is going to be h is equal to the square root of, in this particular case, c squared minus 1/2 b minus a squared. So it'd be the square root of c squared minus this distance here squared, and that would give us the height. H would be equal to 625, which would be 25 squared, minus 49, which is the difference between A and B, 13 squared. I'm sorry. Be 14 divided by 7, divided by 2. I've got to take the half. It would be 14 divided by 2, which is 7 squared. So it would be c squared minus 7 squared, or 49. And then we take the square root of that, and that's equal to 24. So we've determined that h is equal to 24. And so we know from our previous formula about trapezoids that a is equal to b plus a divided by 2 times h. So b plus a divided by 2, b plus a, 26 plus 12 is equal to 38. Divided by 2, which gives us 19, times 24, which is the height that we've calculated. And it's 456 square feet. That would be this area for estimating the area of a trapezoid. Those of you who didn't get that might want to look at it a while, and it'll come back to you. Pythagorean theorem and the area of a trapezoid. Again, here h is equal to c squared minus 1/2 b minus a squared to the square root, and that's the square root, and that's how we came up with our 24 feet. A is equal to AH. This is just another formula that we could use by using our own reasoning. A is equal to AH plus 1/2 b minus a times h, and that's equal to h times a plus 1/2 times b minus a. And so A is equal to 288 plus 168 is equal to 456 square feet. Same thing. We just took the area of the rectangular, h times 2a, or h times a, I'm sorry, h times a, and then we need to calculate the area of these two triangles on each side. And that's all that we did. The average end method of estimating volumes, in this particular case, we'd have to know what is A in order to use our calculations. In this one, we can look at it, we can say, well, we know that we have a rectangle here and a triangle. So if you can't remember a formula, you just break it into two parts, divide and conquer, and we can calculate this. So one area is going to be B times C, which would be this area down here at the bottom. This other area is going to be 1/2 C minus D times this distance here, which would actually be B. So it's kind of easy to figure this one out. So 20 feet is B, C is 10 feet, D is 16 feet. The area is equal to 1/2 B plus A over 2 times H, which is our formula for the area of a trapezoid. Another way to have done this would be just to flip it on its side. And if we flipped it on its side, we can actually another way to determine the area would be B times D minus this area of the triangle over here that we have cut out. So there are a couple of ways to determine this. So A is equal to 1/2 H times C plus D. And H is actually B in this particular case. So it's 1/2 times B, which is 20 feet, times 10 plus 16, or the average of that. So it'd be 20 times 10 plus 16 over 2, or 26 divided by 213 times 20. That's 260 square feet. If we go back, we look at this other one, previous slide here. The trapezoidal formula that we had used earlier had the trapezoid up on its side as compared to this. And some of you might have been able to see that it would apply using that particular formula. In this particular case, just turning it up on its side, and it makes it a little bit easier to use this. So the H here in this particular case would be B, and then we have 10 plus 16 divided by 2, which would be the average area. And 1/2 of that, and that would give us this area of this trapezoid. Again, another formula would be A is equal to C times B, right, plus the area of the triangle over here, which would be A as the hypotenuse, B as the height, and then D is going to, this area in D here is going to be actually D is D minus C. So it's that was D minus C. We have B as our height, so it's D minus C to the 1/2, but divided by 2, I'm sorry, times B is the height, plus the area of C times B, and we come up with the same formula. So you have to use your reasoning in a lot of cases based on your previous geometric and trigonometric coursework. Here we have a formula that when we have a lot of different areas, which is most common, you go along a particular, we're going to trench something, and typically we're going to have to deal with multiple areas because the existing grade is not going to be nice and smooth as we had assumed in the previous examples. Here we have a variant cross-sectional heights, cross-sectional areas. And so A1 is not equal to A2, is not equal to A3, is not equal to A4, is not equal to A5. So we have 5 different cross-sectional areas that are based on using engineering judgment as to where we'll draw these lines. Here in this particular case, it made it nice and smooth because it looks like these lines are from one area, cross-sectional area, to the next, are nice and straight. However, there will be, of course, some variations. We're estimating the volume here, and we're not actually getting an accurate measurement. We're estimating volumes using these formulas. So in this particular case, of course, we know L is going to be this distance between the two areas. We're going to assume that the areas are of equal length. Okay, they're going to have to be of equal length to use this formula. In other words, the distance from A1 to A2 is going to be equal to the distance from A2 to A3, equal to the distance from A3 to A4, and then A4 to A5 to use this particular formula. So we can develop this formula. This VF is our correction that's going to convert it from cubic feet to cubic yards. The formula came out of a manual. I would have just put 27 in there, but no one asked me. So anyway, so we have basically this first section here is going to be A1 plus A2 divided by 2, and then we're going to have plus A2 plus A3 divided by 2. So here we have A2 twice. A2 over 2 plus A2 over 2, just A2. And the same things apply to A3 when we relate A3 to A2 and A4. So the formula is really one that's really easy to develop. And so we have the total volume is going to be equal to the length, L, times A1 plus over 2 plus A2 plus A3 plus A4 plus, in this case, would be A5 over 2, but as the n represents, you can, depending on how many cross-sectional areas you have, you can use this formula ad nauseum. And so if we went, let's say, up to A8, it would be A5 over 2 plus A6 over 2 plus A7, I'm sorry, it'd be A5 plus A6 plus A7 plus A8 over 2. So whichever is the n cross-sectional area would be divided by 2. The beginning cross-sectional area would be divided by 2. The rest of them would just be the areas of the cross-sections themselves. Again, just to reiterate, the volume is going to be the length between A1 and A2, or A2 and A3. These L's have to be exactly the same in order to use this formula. So it's going to be L times A1 over 2 plus A2 plus A3 plus A4, and in this case plus A5 over 2, divided by 27 cubic feet per cubic yard to give us bank cubic yards. Again, bank cubic yards is the soil the volume of the soil in situ in the ground before we take it out, before it's removed. Some cases we're not so lucky to have equidistant areas, equidistant distances between the areas that we're going to cut. In this particular case, we're assuming 150, 151, 152, 153, 154, 155, 156. So our L is going to be 100. We could actually go back and use that formula and plug the formula in to use this. So that would be 100 divided by 27 times 360 over 2 plus 10,200 plus 18,000 plus 23,500 plus 12,600 plus 5,940 plus 400 over 2. We can do that. But another way to do it is, and you will encounter where these distances are the station numbers that are actually used in the calculations may not be equal 100 feet in each particular case, or even equal 150 or equal 200 feet. It's going to be variable. Like from here, from the first station to the second might be 100, the next one might be 50, and the next one might be 250. It depends on the actual grade and how these cross-sectional areas line up based on the engineering judgment. So what we would do is, first thing we do is we calculate the distance between the first station that we're using and the second station, and that in this case would be 100 feet, and 100 feet would go here. So in our first one, it's just the end, so we don't have any volume here at all. So our distance is 0 and our volume is 0, so these would be left blank. So in the next one, our length would be 100, and then the area is going to be the average of 360 and 10,200. And we'd get divided this by 27. That would give us the cubic volume. Here I've actually have it worked out so that we see in each particular case our distance, our L, is 100. Okay, and then the average between 360 and 10,200 is taken, times 100 divided by 27. We convert it to cubic yards. If you do not divide this by 27, you'll have, of course, a much larger number. But we want to divide this by 27 in order to get our actual volume in cubic yards. Then we do it for each different station, and we'll come up with the total volume in cubic yards. Here's a situation where we don't have the L is equal in each case. We see here it's 50, here it's 200, here it's 100, here it's 100, here it's 100, and here it's only 20. Cross-sectional areas, so we're going to have, of course, the first cells at the top for distance and volume are 0. If the distance is 0, of course the volume is going to be 0 because it's the cross-sectional area times 0, or our volume be 0. First place, our difference between the first station and the second station that we're using is going to be 50. Between the next two will be 200. Between the next two will be 100. And between the next two will be 100. The next two will be 100. And the difference between the last two stations is going to be 20 feet. Our area is going to be the average for our first area for our first volume calculation. Our area is going to be the average between 9,360 and 10,200. And then for the next section, it's going to be the average of 10,200 and 18,000. For the next section, it'll be the average of 18,000 and 23,500. Then the next one will be the difference, or the average between 23,500 and 12,600, and so forth, and so on. So we couldn't use that formula that we saw earlier, L divided by 27 times A1 over 2 plus A2 plus A3 plus so forth until we get to N over 2. We couldn't use that formula because our L's are not the same. So you have to be careful if you're taking an exam that you don't just jump in and assume your L. Another mistake people made with that formula is that they assume L is in sum from 149 plus 50 to 155 plus 20. That'll give you a volume that is way too large. So we're going to go back and we'll fill this in where we have our 50, 200, 100, 100, 120, and then we take the average of these areas times our 50 divided by 27, and then we get our volume in cubic yards. Sum them up, and then this is the total bank volume of soil that's being excavated for this particular project, or from station 149 plus 50 to station 155 plus 20. And again, you cannot use the formula L over 27 times A1 over 2 plus A2 plus A3 plus ... plus AN over 2. Sometimes we'll have a mass diagram, and definitions, of course, are going to be cut, the volume of excavation for a given cut. Fill is the volume of material to be added to an existing terrain for a given fill. Waste is a volume of material that is required to be hauled off the site, and borrow is the volume of material that is required to be brought on site. One of the things about construction is we tend to keep our vocabulary very, very simple. As you can see, cut is the amount of material we're cutting, fill is the amount of material we're filling with, waste is the stuff that we have to haul off and bring to another site, so to be wasting that. And then borrow was where we have to bring in material from some other site and put it in place. Why we call it borrow, I don't know, because we're never going to give it back. We're not just borrowing, we're actually taking it, but we call it borrow. Cut, fill, waste, and borrow. Here's an example of a mass diagram, where this is our intended slope, our intended grade, and here is our existing grade. And so the first section is going to be cut, the second section will be a fill, and the third section will be a cut material. For this project to be a balanced project, this line would have to end up here at our grade line. What this is this is the cumulative area of material being removed. So what we can see is we're doing a cut here, and as the cut gets greater and greater, our slope is consistently going up because the area is it's really the integral of this curve up here. This area is growing bigger and larger. As we begin to take less fill as we go along, less cut as we go along, then our slope is going to level off until we cross 0. When we cross the grade point right here, our slope, of course, is 0. So we have a 0 slope here. And then as we go down, then the amount of material in our mass is going to go down because we're subtracting this area from what our previous point was. And so we're subtracting the integral of that area until we get down to, we reach a balance right here. When we reach a balance at this point, our cut and fill is equal. Our cut and fill, are equal. And so we're back to 0. At this point, if we were just from here back, we'd have a balanced project because the amount of cut and fill would be equal. But we're continuing to take more fill. We're continuing to require more fill material. So we'll be filling this area with fill material. And then our slope is going to continue to go up till we cross 0. When we cross 0, then our slope at the bottom for the fill portion will be, of course, a 0 slope. A 0 slope. And then we begin to take cut again, and as our cut is growing, the curve or the slope of that is beginning to continue to go up. So, I'm sorry, I call this the integral. It's not the integral, it's the derivative of this curve, not the integral. So it's because we're showing the slope of it. So in this particular case, this is not a balanced project. This is what we would be called where we required more fill than we had cut, and that means that we would have a borrow project. We'd be borrowing from some other source as we go along. Again, this curve is really the slope of the accumulation of all this. So the slope is the result of these cut and fill portions. Again, here's another mass diagram example where we're taking material, or requiring material, we're providing material, we're requiring material, providing, and then requiring material. So we're looking at the slopes. Again, when our slope becomes 0 up here, we're at 0. When it becomes at 0 up here, our slope again is 0, and so forth. These points where we cross will be local maxes and local mins, as you know. Local max, local min, local max, and local mins. And as we go through 0 again, we have another 0 slope. In this particular case, it looks like this project is, again, that's a fill project. It's a borrow project. It's not a balanced project. We'd be requiring more material because it requires more fill than we're cutting. So again, here we are, it's a borrow project, shown by the red. Fill, cut, fill, cut, fill. And we have a shortage of cut materials, so we'll have to go to borrow and have a borrow project. Please hold your questions. Next week we can talk about any questions you might have on this presentation. It's pretty simple. It's more algebra and geometry than it is any calculus that goes along with this.